Okay, so where we left off, we were starting to talk about some graphs of velocity and of position and how they're related to the slope of these graphs related to, uh, say, like the slope of a position graph was related to velocity, and the slope of a velocity versus time graph was related to acceleration. Now we're going to talk about um, just some sort of diagrams. These might be just like a picture, or maybe in the problem, it's just represented as a dot. Let's begin with that over there. Let's begin with title motion diagrams. And, just going to throw up some real simple examples. The first one is a hockey puck. We're going to just kind of draw out. I'm not going to give any values or anything. It's just for just sort of build some intuition. I have this hockey puck sliding on some ice, and it is sliding at a constant velocity. So it's going to be a constant positive velocity. So I'm just going to put positive v. We have to remember velocity is a vector, so we need a vector sign on top of these. So since it is constant, that means the velocity here is the same as the velocity here, which is same as the velocity here. Okay. Since the velocity is not changing, there's no change in velocity. That means the acceleration is 0. So there's no acceleration on this hockey puck. Now, acceleration is also a vector. So we need this vector notation above the A. So in all cases, the acceleration of this hockey puck is 0 since it is moving with a constant velocity to the right. All right, another example we might be familiar with is if I just throw a ball up into the air. The ball will go up and gradually slow down, and at some point somewhere it'll stop and then change direction, start coming back down. So let me just fill in again. I'm not putting any values or anything in. I'm just going to say positive or negative. Typically, we say things moving upwards are positive. So I'm going to put let me zoom in just a bit. Let me put a positive velocity right here. Oh, that's what I'm missing. I usually do this in blue. Okay. Positive velocity upwards like that. And you see it's going to be a positive velocity until it stops all the way up here. So let me fill that in. Actually, let's go, I'll do each step at a time. So while it's down here, it's being affected by gravity. There is this acceleration that opposes this direction of velocity. That is gravity accelerating downward. I'm trying to make, let's make it a little bigger like that. Okay, so this is, and let me separate it. This is the acceleration that is downward minus acceleration. It's minus because it's pointing downward. So up here, again, we have a positive velocity, but this is going to be a case of constant negative acceleration. This acceleration due to gravity right here is constant everywhere. So at every instant, this ball is being opposed by this acceleration downward. So let me see if I can do this. So it will actually be the same. Okay, so it's being affected there, and I'm just going to fill it in. There's another one up here, and there's another one up here at the very top. So that way I don't have to. You see this is positive all the way up. Positive even at this very last moment until the very top where the velocity is 0. Then on the other side, when it starts coming back down, for that moment when it's at the top, the velocity is 0. And is being affected by a constant negative acceleration pointed downward. Okay. So if we could do this, I'm going to have so many layers to deal with later. All right. And right here as well. See this constant acceleration, slowed it down. But then as we get onto this side of the arc of this ball, it will begin to speed up. This negative acceleration starts to make this a negative velocity. It's very small. This arrow represents how quick it's moving. And it just gets larger and larger, negative acceleration. And there is a point of terminal velocity, and that's just a point of when an object can't fall any faster. And that's because it's hitting too many air molecules that are in the way. And so that sort of balances it out. Every object has its own terminal velocity. If we were in, say, like where there's no air or anything, an object would just keep increasing its velocity until it is affected by something else. All right, those are a lot of arrows around that picture. Let's move on to the next little diagram. Okay, we're down here. This is a situation that has multiple parts. So we saw this constant acceleration in the top right with the ball, and we saw this constant velocity, the top left with the hockey puck. This person on the bicycle is going to experience multiple sort of situations in one. So let me try to show those real quick. So right at the beginning, it is stationary. And I didn't add any arrows on the person on the bike because this is where we can show you, where I can show you that you don't always have to draw this picture every time. What we can do, again, to make a problem simpler is to just reduce the problem, reduce the object to a single dot or a single particle. So I'm going to take this bike, this person on the bike, I'm just going to cram them all into this dot right here. I'm going to say at that point right there, velocity is 0, because at this instance, they're at rest. And since velocity is 0 and they're not changing their velocity, the acceleration is also 0. All right, for this picture, this second one, this person is speeding up on the bike. So I'm just going to make it, a little arrow pointed to the right. Actually, make it a little smaller than that. And this is a positive velocity. So I'm just going to put positive velocity. It's pointing to the right. The direction is important. And since it is increasing, its velocity to the right, that means it has a positive acceleration. Let me make that positive acceleration to the right. Okay, the next three pictures, that is when this person on the bike is just sort of coasting at the same speed. Imagine this is, a perfect world without friction, any of that. So they're going at the same speed in these three pictures here. So I would put this as a dot that is moving at the same speed. Let me try to make the size of this arrow the same for all three of these, just to kind of represent. That's good enough. So we have this larger and constant positive velocity. And these are vectors. Okay. And so the person speeds up until this point and then goes to constant velocity. Since the velocity is constant, acceleration is 0 for these brief moments. 0, 0. Okay. And these last few pictures, they're slowing down. So I'm just gonna make, say, a small arrow like that, similar to over here. And why are they slowing down? Is because they're changing their speed, but it is making them slow down. So they have this positive velocity still pointing to the right, but they have a negative acceleration. Now we can see when the two are opposing, that's when the direction direction will change or gradually start to change. When they're the same, that's when the velocity will increase. Then over here, I think we got it. Velocity is 0. Acceleration is 0. Okay, so a lot of doing problems on your own, it's understanding what's happening, and I am a visual learner, so I always like drawing the picture and sort of seeing if I can figure it out before I actually do any math, if that makes a bit of sense, or at least understand what's going on in the problem. Okay, so we have this new kind of intuition. Let's look at, I have up here constant acceleration downward. What if we want to look at that a bit more? Where is it? Let's look at motion with constant acceleration. So since it is so common that something might, speed up for a bit at a constant, speed, constant rate, and then maybe it's constant at 0 for a minute. There's a lot of times where acceleration can be constant. So let's look into it a bit more. One of the clearest examples is the acceleration due to gravity, or the gravity itself is an acceleration downward toward the center of the Earth. And that's when we all know without really knowing physics. We learn from intuition. The perhaps, like the person on the bicycle, maybe we want to know someone's velocity. I'll just keep the dots. So someone's velocity after they've undergone a little bit of acceleration. What is their new velocity after this, little bit of constant acceleration? That can be something valuable. So what we're going to say is, we know that the velocity of an object, so the velocity in, this one dimension, say we're doing it horizontally, so x, is, however fast or however quick this object was moving to begin with. So v naught x, so this is just saying the initial velocity, plus however fast it is afterwards, or how much it changed by. So delta v. So up here in this case with the bicycle, it starts out with a velocity of 0, and then it ends up with this much larger velocity. So it has this delta v, it changed its velocity somewhere in there. That is the acceleration. So I could rewrite this as the initial velocity. Instead of delta v, I'm just going to say this is how the value of its acceleration times how long it was accelerating. So it is, let me try to make this clear. Average t. Oops, sorry, that's not t, that's x. Multiplied by delta t. So I'm replacing these terms right here, delta v, with the average acceleration for how long it was accelerating. So that's kind of my way of saying I want to figure out the acceleration going on in here. It was accelerating, I know that, and it was doing it for some amount of time. So let's examine that. This is a way for me to introduce acceleration. I need this. And finally, since I believe in the last class, we talked about average versus instantaneous speed and velocity. In here, we can also talk about average and instantaneous acceleration. Since in all of the cases I'm going to talk about, the acceleration is constant, I could say that a sub x, the instantaneous acceleration, is the same as the average acceleration. So that kind of links it back to yesterday's class. Since they are the same, or since the acceleration is constant. All right. Moving on, we will derive some, or not derive, I'll say arrive at some kinematic equations up next. And these are some equations that will ultimately help you do, I would say 90 to 95% of all problems in this chapter, and even future chapters. Okay, so deriving constant acceleration kinematic equations. So since I just talked about the instantaneous instantaneous acceleration being the average acceleration, I could rewrite that thing I just put down earlier with that equation. We can rewrite the velocity of an object. So instead of I had v sub x is equal to v naught sub x, and this is where I had the a average, average acceleration times time. Instead, now I can put the instantaneous acceleration, so a sub x times time, like that. Remember that the acceleration is constant. So it could be constant at 0, or it can be a constant positive or negative value. It's just being held at a fixed value. Like that. What if, this is a good way to find the velocity. I can see how fast an object's moving, looking at this equation up here. Actually, in fact, before I move on, let me put a star next to this one of the kinematic equations. So this is helpful in finding the velocity and how it changes if given the acceleration and how fast it starts and the time that accelerates, I can find out how fast it's moving at the end of this period of acceleration. What if we want to find the position? How far does this object move while being accelerated? I can do this with kind of some, graphical answers. First, I can instead back up a bit. Let me assume that the velocity is constant. So in these two cases down here, the velocity is held constant. So let me go like this, so you still see that at the top. So we have the velocity in this one instance up here is held constant at a positive value. So it's above 0. And over here, we have velocity held constant at a negative value. These are just two separate graphs. Let me sort of do a bullet point what I'm trying to achieve. So if the velocity is held constant, if the velocity is constant, it is a flat line on a velocity versus time graph. We can see that from these two graphs. Oh my goodness, I keep pressing. This happened yesterday. It's getting, there we go. It is a flat line on a velocity versus time graph. Okay. Something else we should know about these graphs that I'm, just throwing at you. You just seeing all of these graphs within the past 2 days. One thing to know about a velocity versus time graph is that the area under a velocity versus time curve a velocity versus time curve. In this case, it's not a curve, it's a flat line. Is the displacement. Delta x. So that makes these graphs actually very valuable. I can, if I didn't want to do all of this math, maybe some calculations are a bit too difficult, or, for some reason, I can just find the area under this curve. So right here, this positive velocity, the area under the curve from, say, time 1 to time 2, that's going to be this delta t. The area in that specific region right there, that is the change in position. Just that area right there. So what is the area of a rectangle? Well, it's just the length versus the width. Let me put right here also inside. I'm going to say this is a positive area. And I can, address this one. This is also the same thing. So the area under the curve, this is not, it's going to be this area right here. You see, this is going to be a negative velocity over here. It doesn't mean you get a, a huge infinite rectangle over here. It means under in this manner. Hopefully that's just clear enough to see. So this is a negative area. So since it is just the area under the curve, we can do this easily with these constant velocities. This is just the area of this rectangle. So we have delta x is the area under the curve. That's going to be the height, which, looking at this one, is v naught x, v naught x times the change in time, so delta t. And I forgot to put on these, forgot to label these graphs. Oh boy. Oh, it's okay. How did that pop up? All right. So we have, where are we? We're right here. Nope. I brought up the text tool and that's not what I wanted. Okay, there we go. So we have delta x equals the initial velocity times delta t. Next up, what if the velocity isn't as simple? What if it's not this straight line over here? It's not just an area of a perfect rectangle. What if the velocity is something like just we're not going to jump to too complex. What if it's a sloped line? And we want to find the change in position from time 1 to time 2. So I've represented that with these dots also. It's speeding up. It's gradually getting faster from velocity 1 to velocity 2. within this, span of time. That is where we can break this up into manageable sections. So before I put anything else down, I'm going to say for a velocity versus time curve, that is not, or I could say that is more complex. Break it up into manageable sections, or break it up into sections. Okay, so we have this curve. How can we break it up into manageable sections? Well, I've pre-done some dotted lines to help us out. So from time 1 to time 2, we have this extending up until it hits the slope. And we also see that now that we've broken this up, we have this rectangle right here. And we have a triangle. Those are easy to deal with. We can find the area of the areas of those separately. So we just need to know the width of this rectangle down here. So that's T1 and T2. That whole thing is just delta T. Now we need to know the height. Well, the height is up here. It's right to the top here. That is just V1x. And what is this little sliver right here? What is the height of that? Well, that's the amount of velocity it changes over the amount of time. So it's the difference between 2 and 1. That's delta V x, which is, I could say underneath is 2 minus 1, or let me bring the acceleration into this, factor it in. The acceleration times time. All right, so now we have these two manageable sections that I can add up. Let's add up the area of each of these things. Add up area of each section. Okay, so we have this rectangle. The area under a curve is the displacement. That's what we're trying to find. So the displacement is the area under the curve. That's the rectangle. V1x times delta t. So that's this area. Plus area of a triangle. Okay. And it's delta t squared because there's delta t on the base times height. 1/2 base times height. And we could clean this up a bit if we set T1 equal to 0. Usually when you do an experiment, you start the experiment, you start the timer, and it starts at 0 automatically. So we're going to set t1 equal to 0, and we're going to set t2 just equal to t. What we have is x minus x naught. That is this delta x equals v naught x. Let me make it clear. Times time plus 1/2 instantaneous acceleration, and it's a constant value, times time squared. All right, I'm going to put a star next to this one. This is another kinematic equation that is very useful in solving almost anything. There we go. Okay. Now look at these two equations I put a star next to. They both have, a lot of variables in them. I would need to know, say for that top one, I would need to know, initial velocity, acceleration, and time to find that final velocity. And the one on the bottom is even worse. I need to know time, initial velocity, and acceleration, and the initial position in order to find out the change in position. So these are very, I'll say these are very powerful tools, but you need a lot of information for them to work properly. What if we don't want, or maybe we don't have all of that information? We can find a different way of making a kinematic equation. So let's go to the next one. All right, so what if expression that does not depend on so many terms? So we will start with those two equations I have just listed. And we're going to just kind of plug them into each other and solve for t. And it's really me just walking through a couple steps. At the very end, we will get something valuable. So let me just sort of go through this real quick. We're solving for x, and we're plugging one equation, I believe this equation, into the other into the other one. X, and we have v of x oops, sorry. All right, so that's what we're doing. We're solving for t in this one and plugging it in over here. And v naught x. Oh, sorry, we're solving for t right here and plugging it in over there. Okay. Then multiply by both sides. This is really what we're doing. Multiply both sides by this is the sort of the bit of derivation that we're doing. Right, 2ax. So now we have 2ax delta x Vx minus V naught of x plus Vx V sub x minus V naught of x. What we're doing is we're trying to, we have solved for t in this, so it's was t equals Vx minus V naught of x divided by a x. I just, want to do every single step. So we did this, and then we're multiplying everywhere there's a t in here. That's where we're putting this equation. We're doing this to maybe get rid of the t value, the time. Maybe in some problems we don't have time, the amount of time that something is happening. So this is our way of simplifying those kinematic equations. Simplify. V of x squared V naught of x squared 2ax delta x. So this is a kinematic equation. I'm going to put a star next to that. Since we've solved for t earlier, it just vanishes in this final version. And this equation right here is also perfectly fine to use. And it's actually very helpful when we don't have the time value. And this last one is, I'm not really going to derive as much. I'm just going to kind of reason my way through. We can look at the average velocity. So let me go like, try to find a good, all right, let's go like that. We can look at the average velocity of that previous example. And in this case, the area under the curve is this highlighted blue region. Well, what if we were to do the average velocity? That's not going to be something that follows this path exactly. If you remember what average velocity was, it was just sort of, you take the beginning and the end, and it's just a real rough estimate of what the velocity will be. So if I was to find the average velocity of this case, the graph would look like this. Zoom in a bit now. And by doing this, we have the same area underneath the curve. It's because this is a very simple graph. It's just a straight line. We have the same area under the curve. This amount that's sticking out over here is the same as the amounts missing up here. Okay, so we have the average within the x direction. That's just, final plus initial divided by 2. So you take an average of anything, it's just the number of things. So 2 things added together divided by how many there were. How can this become useful though? Well, this is a way to find the average velocity. Hopefully at this point we can see that we can make a way to find displacement. We could say delta x, it's the area under the curve. So I'm just going to be average x delta t like that. But we know v average is this thing. Okay. 1/2 times delta t. Okay, that is another valuable equation. So use this. I'm also going to say this average average velocity is useful to know also. But this one that I put a star next to is another kinematic equation. So we just sort of put all of these 4 equations on the same page, sort of a reference sheet for you guys later. So here are the kinematic equations of motion. They can be used with nearly any one-dimensional kinematic problem with constant acceleration. That's the important part. So it could be constant at 0, or it can be constant a positive or negative acceleration. You can use any of these equations. Put it down, and I'll write a little thing about them. Need to. Okay. They're not specifically named or numbered. You might see them in a different arrangement in other places, but these are the basic ones. And in fact, this bottom one, I should go like this because this is actually what we're looking for. To do 2x times delta t, like that. Okay, now I'll write a little thing about them. Okay. The first one you can use if you're not interested in the position. If you don't need the position, you don't have to have it in the equation. Not interested in position. Second one is very useful. I would say very useful. Just a little note. But you need a lot of the variables. You need at least 4 of the 5 variables. That means you can, if you do have 4 of 5, you could solve for any of the other one that is missing. This one right here. If you're not interested in time. And the last one, if you're not interested in the acceleration. And that is just the equation for velocity. So quick note on this bottom one. If it is a constant velocity, you can see if it's constant, this would be v. And since it's constant, that is also v. So it's 2v. And 2v divided by 2 is just v. So this is just the equation for velocity. So there's no acceleration in this term. Something that we can remember. I'll just say like, also remember just in general, I made the point about this being the equation of velocity. We'll just put the equation down here. That is, we'll just say v of x is d. And if you look at the equation at the top, this one up here, this is just final minus initial equals acceleration times time. So that's delta v equals acceleration times time. This is just the equation for velocity. So let me put that down here also. Okay. Just kind of going in circles with these, but they're all useful, and you don't want to have to like rederive or figure out what the equations are. So that's why we kind of highlight these four in this arrangement. Go on some examples, and then we're pretty much done with this chapter. Right, so in the last sort of bit of this chapter, there's a section on getting these equations by integration. So it's not with sort of graphs, sort of looking at the area. I had some really nice, flat lines, a nice curve. You find the area underneath. In sort of real life situations, you might have, a very complex velocity versus time curve. So finding the area underneath a very complex curve requires some calculus and some derivatives that are infinitesimally small. The problem is that once we have these equations, it's kind of sort of retreading over this again, and I need to keep moving with the pace of this course. So if you were interested in the integration method, I'd say look in the book, and it's right at the end of this chapter, chapter 2, and you can see how you get to all of these equations through integration. Right, so with that, I'm going to move on to some examples using these equations, and then that will be the end of chapter 2. So let's go to our first example. Also, this is the end of chapter 2. So this is the end of the material for the homework and the end of the material that's going to be on the quiz on Monday. So hopefully I've given you guys all of the tools you need to figure that out. If you, after these examples, if you're still having problems, you can always email me, let me know, or you guys in class, you could ask me afterwards. So let's go on the example. Okay. So for this first one, you are driving on a highway at night and you see a car in front of you that is stopped for some reason. It's stalled and you brake to stop your car. As you are braking, you're braking at a constant rate of 5 meters per second squared. So the questions that we're going to ask is, what is your car's stopping distance? So how far of a distance will it take from right when you start, right when you push on the brakes to right when you stop? How long is that going to how much distance are you going to cover in that time? The second question is, how long will it take for your car to stop? And the third question is, how far does the car travel in the last second? That third question is, I was thinking of not having it in this example, but we'll see how it goes when we get there. So what I like to do is always start out with a picture. So I'm going to go this. Let's draw a picture of what's happening. Okay, so we start out, so we're going at some speed earlier, and right when we start pressing on the brakes, that's right when we start this situation. So that is going to be our origin or position, initial position, x naught, that's equals 0. And we know that right when we are moving this way, also, we don't have to draw a whole car. We can just summarize it as a dot. We know that right as we are starting to press on the brakes, our velocity was 30 meters per second. So our velocity right when we start, right at this point right here, was 30 meters per second. And I'm going to emphasize that this is a positive 30 meters per second because it's going to the right. Okay, let's say I'll just put like down here, that's our acceleration. The change in velocity is we're going from, some speed to 0. So we're reducing that value. So it's going to be an opposing acceleration. So the acceleration, let me put velocity up here, equals acceleration equals a negative 5.0 meters per second squared. Now that negative isn't in the question, in this value, it was in me understanding what is happening. So negative acceleration, so the car is decelerating. And at some point over here, the car stops. And that's going to be our final position. Okay, and I'm just going to draw this final position. So when the car gets all the way over here, it will be completely stopped. So the velocity at the final position is 0. So let me put over here on this V, I'm going to put V naught x, because that's our initial velocity in the x direction. Okay, that. Let's find that first. Let's solve that first problem. What is the car's stopping distance? So we need a kinematic equation that has the distance. So we need to solve for distance. We need to solve for distance. Let me put this right there. So for that first equation, We need to solve for delta x. That's what we're looking for. Which kinematic equation can we use? Well, there is, I'm just going to go on the number that I've given you guys, these equations. We could either use that second one, or we could use the third or fourth one. Okay, so we have three options of kinematic equations we could use. One of them doesn't have acceleration in the term. That was that last one. So we could get rid of that. One of them needs a lot more terms. We don't know the time yet. So we could get rid of that second kinematic equation. So we don't really know the time, and we don't have all of the pieces for that equation. So what we're going to use is, we're going to use this one that happens to be the most useful for us. V of x squared oops, sorry. Okay. Now here, the sub indices, you could just think of it as final and initial. So up here we have a final velocity of 0 meters per second. We have an initial velocity of 30 meters per second squared plus 2 times this acceleration. We are changing our velocity. It's a negative 5 meters per second squared. And we have delta x, so change in position. Okay, since this delta x is what we're looking for, we could rearrange this equation so delta x is on one side by itself. So actually, we can solve for delta x. I don't need to do every single step. X equals 90 meters. Okay, so solving for this is just, subtracting things over, dividing this over to the other side. All right, so we found the distance it takes for the car to stop at this rate. Now, how long does it take to stop? Can we use the same kinematic equation? This one right here? We can't, because there's no time in this equation, and we need to solve for time. Sort of jump to the answer on which one we're going to use this equation. And a lot of solving the problems is just sort of trying an equation out and seeing if it works for that specific problem. There's a lot of trial and error on figuring out which one might work. Okay, so it's via x. And in this instance, we know a final velocity. Final velocity is when it stops over here, and that is 0. Its initial velocity was positive 30. It had an acceleration of -5. And there's the time. We need to solve for time. So just like the problem above, we could solve for time. It takes time it takes is 6 seconds. And I did it again. The last question, let's see, we have 5 minutes. I'm going to skip that last question because it makes a little bit of an assumption that I don't quite like. I could maybe reason through if I had more time. I have to redraw another graph. I'd say if you want to look up that last question right here, you can look in the book. I can also add the steps for this one. I'll add it in the notes for when you guys look at the notes later. They'll be in here. I also ran out of room. Okay, so let's move to the next question real quick before I run out of time. Okay, another example, and this is the last one. So upon graduation, a student throws their cap into the air. And we're going to assume that the velocity that they throw their cap into the air was 14.7 meters per second. And it's pointed upwards. We also know that there is an acceleration from gravity that is pointed downward. And that acceleration is 9.81 meters per second squared. So in this question, what we're looking for is how long does it take for the cap to reach its highest point? What is the distance to the highest point? And if throw the cap in the air and you catch it at the same height, what is the time it takes for this complete path that the cap travels? Okay, so starting out, let me draw a picture real quick. Okay, we're going to have an initial height we'll call y0. And we're going to be transitioning into 2 dimensions. Things moving vertically up and down, we're going to change it from x to y. And you think of them as just going back and forth in those kinematic equations. You can make them an x or y, depending on just like the direction you're using. So this is initial height. Why not? And this is the final height. Y final. So it starts out, the cap starts at this position and is traveling upwards with a velocity, initial vertical velocity. So velocity in the y direction of 14.7 meters per second. And we know that when the cap is at the very peak, it's going to be, it is F and then Y. V final Y is 0. So this is just something that we can put in because of intuition. We know that at the very top, it's going to stop moving upwards. For the briefest moment, the velocity will be 0. And it will have a constant downward acceleration of minus 9.81 meters per second squared. So I'm specifically making it minus because it's constantly downward. So what is the, how long does it take for the cap to reach its highest points? We're going to use a kinematic equation. Y feet initial in the y direction. This is just about the same as the previous, example, but we're sort of expanding it to see what it looks like. Y direction. So the time, solve for the time. Since it starts at a initial height, or I'm sorry, since it has a, oh my goodness. Since it has a final velocity of 0, we have 0 minus over y. We have minus 14.7 meters per second over minus 9.81 meters per second squared. The time it takes to reach the top is 1.50 seconds. Okay, what is the distance to the highest point? So distance, I'm going to end up using this equation right here. Delta y equals v average in the y direction times time equals 1/2 initial velocity in the y direction plus final velocity in the y direction. That's t. And just plugging values in here, we get 1/2 14.7 meters per second. That's starting velocity plus its ending velocity, and multiplied by how long it took to go from the bottom to the top. 1.5 seconds. We get a result of this cap went up 11.0 meters, 11.0 meters. And the last bit of question, assume the cap is caught at the same height. Was the total time the cap was in the air? So we're going to use that third kinematic, or I'm sorry, the second kinematic equation. Delta y equals v naught y time this one. Go like that. So its change in height is going to be 0 because it started here, then it went all the way up, and then all the way back down to the same exact height. So its displacement, its delta y right here, its change in height is 0. That means that makes a lot of this, the rest of this problem easier. So then we have v naught y plus 1/2 acceleration in y times t. And I'm factoring out a t of both of these. I'm going to put it on the outside like this. Why am I doing that? It's to see that there are two answers for this problem. So we're solving for t, but there are 2 right here. That means we need to this is a quadratic. We'll see that there's a answer at t equals 0. So t, I can just divide this over and t will equal 0. That's the starting position. And we know it's a starting position because we usually start the timer at 0. And that's right when we sort of launched it upwards. So we don't quite want that answer. That's not useful for us. We want to know how long it took to go from this height up and then back down to this height. So solving for the other answer, we get, need a bit more room, minus 2 v naught y over a of y minus 2 14.7 meters per second over minus 9.81. And here we have our results that the time it takes is 3.0 seconds. Okay, so went just a bit over, but this is the essence of solving any kinematic equation problem. You have your tools, you're able to solve for these now. Hopefully I made it clear with these examples. There were tons of examples in the book. I sort of, spliced a couple together. So if you're having problems and you want some more examples, I'd say you could check out the book. If you guys have more questions, you could always, ask me later also. Other than that, that's all I have for today. So if you have questions, you could stick around and let me know. Otherwise, I'll see you guys later.